Hello and welcome to CH342. This is Computer Applications and Instrumentation. So I'm Udayan Ranatunga and I'll be teaching you all of this course. This is a 2-credit course, but before we start on the course proper, I'd like to just spend one video on talking about motivation, why we're learning this course, and a little bit about the outline and how we're going to actually go about learning it. So let's start with a little bit of history. If you look at the history of mankind, of human civilization, you'll see that we've slowly developed, but there have been points in time where the development has very rapidly increased. And this has usually been seeded by some sort of discovery or by some sort of scientific invention. So the discovery of the lever allowed people to push, pull and lift objects that were much larger than themselves, and this became how cities were built. The invention or the discovery of paper allowed people to write down knowledge and then stop being hostage to just oral history. Then the printing press came along in the 1500s, and this changed everything because now you could mass produce knowledge. That means what one person found out or what one person discovers, one person knows, can be spread out to the masses. And this is when science really started to take off. And after that, we've had the discovery of electricity, of the combustion engine, and all of these things have changed life as we know it. Now, the focus of this course is that we're actually living in one of these points in time where life is changing as we know it. The computer was invented in the 1950s, but in the last 70 years, it has seen such a remarkable development, and it has become such an integral part of our community and our world. It is changing everything. Computers are now a part of day-to-day life. They're in your pockets, in the cell phones that you use, on your lap, on the laptops that you use. They're in fridges, in cars, they're in manufacture, they're in medicine, they're in agriculture. Everywhere you turn, computers are playing a part. And this is the motivation of this course. We are living in a time of unparalleled change. Discoveries are coming faster than ever before. People are getting more connected than ever before. And more than that, every single person has much more individual power than ever before. And learning how to use this power and learning how to use this knowledge, this technology, is integral, or it's so important in your future lives. So I'm hoping that this course will expose you to some aspects of how computers are used specifically in chemistry, but I hope that it will motivate you just to learn more about computers and how computers are being used in the world today. Now, just to put into context how much computers have improved during the last 70 years. The first computer that was developed, the Manchester TC, this was in 1953, and it had 92 transistors and 550 diodes. Now fast forward to 2019, and AMD came out with the Ryzen 2 microprocessor, so a small microchip, and in this microchip there's 38 billion transistors. So we've gone from the Manchester, which is half a room size, which had 92 transistors, to a 1-inch by 1-inch microprocessor which has 38 billion. There is no other field in the world which has seen an increase or development in this scale. The best illustration for how quickly computers are developing is probably Moore's law. Now Moore's law is an observation saying that the number of transistors that you can fit on a microprocessor seems to be doubling every 2 years. So if you have a processor with, say, a fixed size, the number of transistors that you can fit on that seems to be doubling every 2 years. Now, the number of transistors is somewhat proportional to the number of calculations that you can do. So, doubling the number of transistors means doubling the number of calculations you can do for that same size of chip. as you can see, Moore's law seems to be holding true for the last 50 years. This graph shows the number of transistors on the y-axis, and that's a log scale, while the years are in linear scale. So you can see that there seems to be a linear relationship here. But can you think of any other field where this sort of development or improvement happens? So just imagine if you had this sort of development for cars. You could buy a car which is twice as fast in 2 years' time for the same amount of money. If you think about it in terms of clothes, you should be able to buy twice as many clothes for the same price in 2 years' time. And there is no other field that I can think of where you have this sort of improvement. And this is the reason why computers are being progressively more, they are being used in many more fields. So they're getting into more fields, and they're getting used more diversely and more extensively in all of the fields that they are being introduced into. So this next slide actually shows the number of calculations per second per $100. Now, what I like about this graph is that right now you can see that the calculation levels that are coming, right, are slowly pushing past into the region where the number of calculations is approaching those of biological systems. So the computers have already passed the number of calculations per second per $100 of a mouse brain, and they're slowly coming into the region where we're reaching into the number of calculations that are done by a human brain. And perhaps this is why you're seeing more and more artificial intelligence and machine learning applications which seem to be very close to what we humans can do as well. Now, computers are getting faster for the same price, they're getting smaller, and that means that they're being used in many different fields. This is true for chemistry and science as a whole too. So when you think about how computers are used in chemistry, you can classify this in three major areas. And the first is computer-aided chemistry. Computer-aided chemistry is when you use computers to help you do experiments. So if a computer is controlling the machine or instrument that you're using to take a measurement, or if a computer is plotting out readings, or if it is analyzing readings to give you interpretations, these are all you can classify as computer-aided chemistry. Now, the second way that computers can be used in chemistry is through computational chemistry. Now, in computational chemistry, what we're doing is we're doing experiments virtually. We're actually doing experiments inside the computer. So, with computational chemistry, you can test theories, you can predict behavior, or you can also study mechanisms. Now, the final way that computers can be used in chemistry is in cheminformatics. So, cheminformatics is basically using computers to search vast amounts of data and look for patterns in that data. So, we're talking about data which is so large that it would be impossible for a human to go through rationally. So, such things as data mining, quantitative structure activity relationships or quantitative structure property relationships, QSAR and QSPR, and machine learning, artificial intelligence used in chemistry, all of these I classify as cheminformatics. So, I should note that this classification is not a very strict one, and this is just my own way of classifying the uses of computers in chemistry. Okay, so let's also talk a little bit about the outline of the course. So in this course, you'll be doing 3 sections. The first section is digital electronics, and here you'll be looking at the fundamental building blocks of computers, which are electronic devices. So we'll be talking about Boolean logic, and then we'll be talking about gates and combinational logic circuits, and also sequential logic circuits which have flip-flops in them. In section 2, we'll be looking at interfacing. So interfacing is when you connect a computer to some external device. So this could be if you want to control an instrument or equipment or some other sensor with a computer. Particularly, I'll be focusing on microcontrollers and the Arduino microcontroller in particular. That's section 2. Now, in the last section, this is section 3, this is computational chemistry, and we'll be looking at virtual experiments, and we'll be focusing on 2 parts. This is molecular modeling and electronic structure calculation. So this is a little bit of a strange year. So usually the section number 1, digital electronics, is face-to-face, and we do a lot of questions in class. So we'll still do the same, we'll still do a lot of questions, but most of these lectures will be online. Section number 2, this interfacing, we usually do at least 2 or 3 practical sessions. So these are 2-hour sessions, and it's very hands-on. So again, unless we go through a very big change, we might not get the chance to do these practical sessions, but we will work in some way of getting you exposed to microcontrollers and coding microcontrollers, and at least having some simulated practical experiments. Finally, the third part, which is computational chemistry. So this part is actually also very hands-on, and this is probably very well suited for online learning. In the computational chemistry part, I will be giving you lots of demonstrations, teaching you a little bit about theory, but mostly you'll be working with your own computer, and you'll be doing a lot of calculations, a lot of simulations, modeling, and quantum calculations as well. And all of these are very fun. So far as the examination goes, for the interfacing part and the computational chemistry part, I'll be giving a lot of assignments and quizzes, so you'll be getting a lot of continuous assessment, and a majority of your grade will be through continuous assessment. For the final exam, 60% of the final exam will be given from the digital electronics part, and less so from sections 2 and 3. So I hope you find this course as interesting to learn as I find interesting to teach. All of these are very applied and hands-on subjects, so I hope that you find some interest in them, and I hope you pursue your interest even further, and I will see you in the next class.